Section 20.2, we are going to deal with electric force. Now, as I mentioned in Chapter 20, electrons and gravity kind of interact very similarly since they're two forces. We're dealing with, instead of the force of gravity, we're dealing with the electrical force. So we can kind of figure how much force there is between two electrons that have different charges, or a proton and electron, or a particle with a positive charge and a particle with a negative charge. So when we're studying forces on charged bodies, remember, there's only two types of charges, positive and negative. Just like gravity, the distance is going to matter how strong the force is. The closer the distance, the stronger force. The farther apart, it won't be as great. So that's kind of 2 and 3. And again, to hit home here with electrical charges, positives repel positives, negatives repel negatives, so likes repel one another, and opposites attract. And we can do a real quick demo here in class, which I'll show you, but I'll also draw it on the smartboard here with an electroscope. And what is an electroscope? An electroscope is a metal knob with two thin metal pieces of foil attached to it to determine the charge of an object. So an electroscope essentially looks like this. We have a kind of a metal rod with two pieces of foil attached to it. But here's kind of the important thing. When it's not charged, we have positive and negative charges equally mixed throughout this. All right. Now, what we can do is I can charge an object. I can rub charges on a particular object. So if I take a glass rod with silk, I will strip it of a particular type of charge, either positive or negative, and I will leave one type of charge on the end of that rod. Same thing for fur and a rubber wand. I can strip all the charges off of it. I can strip all the negatives away. All I'm left with is positives. So what I do here is, let's say I have a rod. All right, I've stripped either glass or rubber, it doesn't matter, and I have induced a huge positive charge on the front end of that one. What is going to happen? All right. Now, what is going to happen is all our negative charges are going to be attracted to the top. And what is going to happen to our positive charges? They're going to be distributed at the bottom. But now, since I have all my positives at the bottom, what's going to happen to the two metal foils? Well, remember, opposite or likes repel. So what's going to happen is these two branches on my electroscope are going to repel as far apart from one another as possible. It'll kind of show you the idea of that in class. So that is an electroscope. What we can do here, oops, excuse me, wrong slide. What we can do here is there's kind of two ways we can introduce charge to an object. We can introduce it by conduction, or we can introduce it by induction. Now, conduction is charging it by touching it. How many of you have ever taken a balloon, rubbed it right on your sweater, and then you've seen what the static electricity kind of does build up on the balloon? That is doing it by conduction. Or drag your feet on the carpet to build up charge. That's conduction. Induction is charging an object without touching it. After you've dragged your feet on the carpet, what do? You like to go up to somebody and transfer that charge, but you usually don't touch them. You get real close, but you don't touch them, and that charge transfers. That's induction. Induction is kind of how lightning works, too. You will have a cloud build up charge, and you have a beautiful homestead here. And what will happen is you'll have a cloud build up charge with a positive. Well, what will that do? That will draw all the negatives to the top of the house or the object. And what will happen over time is lightning strikes. Okay, that's kind of charge by induction. A little bit. So the dragging of your feet on carpet with the static electricity is perfect. But when we talk about forces, There's an equation that we can use to calculate the force of an object when we're dealing with electricity. An electrical force, you'll see that this is kind of similar to when we were comparing two planetary objects. We took their masses with a constant, gravity, and divided by their distance apart. Now we're doing the same thing, except instead of taking the masses, we are taking the charges of the particle. So Coulomb's law, and Coulomb is a physicist who studied intensively in the field of electricity, comes up with force is equal to K times Q1 times Q2 over R squared. K is Coulomb's constant. So it's a constant. It's never going to change. It's 9.0 times 10 to the 9th. Q is the charge of our particle 1. Q2 is charge of particle 2. And R is the radius between them. Now we're dealing with forces, so what unit is our distance always going to have to be in? Meters. So remember to have it in meters. So we can figure out the force of any object. Force is equal to force is equal to K times Q1 times Q2 over R squared. Now, sometimes it'll give you the force or the charge. Sometimes it won't. One thing to mention on the bottom of the screen there is it might say one electron's attracted to something else. Well, the charge of one electron is 1.6 times 10 to the 19th coulombs. So one electron is 1.60 times 10 to the negative 19. So something to keep in mind. So if we are going to look at this equation, Coulomb's law, our force equation, we can get two questions here. And really, let's just do the first question. I really want to focus on the first question, then we can write down the second one. So if we go ahead and look at the first question, sphere A has a charge of 6.0, UC. What's UC? Remember, UC is microcoulombs, is located 4 centimeters from sphere B with a charge of negative 3 microcoulombs. So one thing we know right away, we have a positive charge and a negative charge. What are they going to do? They're going to be attracted to one another. What's the force at which they are going to be attracted to one another? Well, let's go ahead and solve for this. We know Q1 is positive 6.0 times 10 to the negative 6 coulombs because it's micros 10 to the negative 6. Q2 is a negative 3.0 times 10 to the negative 6 coulombs. We know K is a constant. That's 9.0 times 10 to the 9th. And our R is 4 centimeters, which is really going to be 0.04 meters. So if we go ahead and plug this all in, force is equal to K times Q1 times Q2 over R squared. We plug in our values, 9.0 times 10 to the 9th times 6.0 times 10 to the negative 6 times negative 3.0 times 10 to the negative 6 divided by R squared. R is 0.04 squared. And we figure out that the force between these two is going to be negative 101. But if we do sig figs, it would be negative 100 or negative 1.0 times 10 to the second. And our unit for force is newtons. So that's the first part of this question. The second part now is I have sphere A and sphere B. Pretty easily, all right, we just deduce that this will be attracted at a force of 100 newtons. What, though, would happen if I added a third force or a third particle to this equation? We already know that we're attracted here. We know, since I have two particles of the same charge, there's most likely going to be a repulsion. But how much is that repulsion going to be? So a third sphere, C, has a charge of 1.5 microcoulombs, positive 1.5 microcoulombs, is added to the configuration. If it is located 3 centimeters directly underneath A, which I added in the diagram, what is our brand new force on A? Well, now we have two forces acting on A. We have the attraction from B and the repulsion from C. In the first part of the problem, we already figured the attraction to B. Now we need to figure out the repulsion of C. So let's go ahead here and figure out the repulsion of C. We're going to use Coulomb's law again. So we are going to use the force is equal to K times Q1 times Q2 over R squared. We're going to go ahead. I'm going to plug in those numbers. Q is 9.0 times 10 to the 9th times Q1, which is sphere A, which we know from the initial problem is positive 6.0 times 10 to the negative 6, times Q2, which is C, 1.5 times 10 to the negative 6, over R squared. They're 3 centimeters apart, so R is going to be 0.03 squared. And we figure out this force, again, with sig figs, 2 sig figs, we have figured out that it is 90 newtons. Now, that is not the answer to this problem, because we want to figure out what is the new force on A. Well, A is attracted to B, but it's repelled from C. So what we have is, again, to reiterate, we know that we are attracted 100 newtons to B, but we are repelled 90 newtons from C. So what we're going to have to do is we're going to have to figure out R and this angle. So this goes back to doing our triangles and our forces that we did way beginning in the early of the year in chapters 4 and 5. So we go ahead and do this. R squared is equal to A squared plus B squared. That's equal to 100 squared plus 90 squared. We do our math, and we figure out that R ends up equaling 130 newtons. Lastly, we need to figure out our angle. Remember, tangents are angle. This is an angle we want to figure out. Tangents equal to opposite over adjacent. So what we're going to have to do is the inverse of tangent to the negative 1 of 90 over 100. And we just figured out that our angle is 42 degrees. So what we just solved for is our new force is going to be 130 newtons at 42 degrees, and this is our 42 degrees. So that will be the force that A feels when both B and C are present. So it's very similar to what we were doing with forces and gravity and planets. The equation's the same. We're just changing a few different things when we're dealing with electricity. So we're dealing with charge instead of mass. So you will have a few questions on Coulomb's law for your homework tomorrow.